we're in section 11.3. So we want to talk about slope as a limit. So what we're talking about today, our idea today is we want to talk about tangent lines to a curve. So when we talk about a tangent line, what do we mean when we say it's tangent? What does that mean? If you think back to geometry and you had something that was tangent to a circle. Touches at exactly one point. So what we're interested in, if I were to draw some generic graph here, when we're interested in, now let's draw a parabola here. If we're talking about the tangent line, we're talking about the line that intersects this graph at one particular point, one particular x value. So if I were to draw the tangent line here, that would be a tangent line at that point. And what we're interested in today is the slope of that tangent line. So this line is intersecting the curve at exactly one point right there. And we want the slope of that tangent line. Now, one thing to be careful with, just to contrast maybe the way you talked about it in geometry, is if we have some function that like a sine function or a cosine function, our tangent line can intersect the curve in more than one place. So if I had a function like this, the tangent line at this point is going to intersect the curve in more than one place. So our tangent lines can intersect, just to contrast with a circle. Our tangent line can intersect the curve in more than one place. But we're interested in the slope of the line right there at this point where it's just touching the curve. And the reason we're interested in this is the slope of this tangent line if this curve were describing the position of some object in relation to time. The slope of the tangent line would tell us the velocity, the speed of that object at that particular time. So the slope of the tangent line would give us information about this object. And finding the slope of the tangent line is one of the two major things that you do in calculus. One of the two main ideas in calculus. So the slope of this tangent line, we call that the slope of the graph at that particular point. So let's talk about how we're going to bring in the idea of a limit here. And we talked about it a little bit the other day. So slope as a limit. So we'll draw a graph here to get to the idea that we're talking about. So here's my graph, some kind of graph. And to get to this idea, we're going to pick a point here at some x value. And then we're going to move up here by h units. So this would be x plus h, whatever h is. At this point, our y value is f of x, and at this point here, our y value is f of x plus h. And we're going to connect those 2 points with a line. So here's my here's my line. We call that line, let me do a little better job drawing here. We call that line a secant line because it intersects in two places. Well, the slope of this line equals, well, the rise is f of x plus h minus f of x. That's how far we've gone up. It's a difference in the y values. And the run is h. That's how far we've gone left and right. So that gives us the slope of that line. And what we want to do is let h become smaller and smaller and smaller. So what we're doing is we're finding a point here, and finding a point here, finding a point here, finding a point here. The equations of the equation of the slope of that line is the same, just h is becoming smaller and smaller and smaller. As h becomes smaller and smaller and smaller, we get closer and closer and closer to the slope of our point at that particular line. So we're moving this point further and further this way. So our line, we're getting a bunch of tangent lines, and eventually, as h becomes really, 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 really small, we're really, really, really close to this point, and our slope is really, really close to the slope of the tangent line. So we're saying as h gets very small, we have a limit. We want to know what the slope of the tangent line is getting close to as h approaches 0. As we get closer and closer and closer here, we get closer and closer and closer to a point there. So the slope of the tangent line at x is the limit as h approaches 0 of f of x plus h minus f of x over h. So we're letting h get smaller and smaller and smaller. We're calculating our slopes. And as h approaches 0, our slope, the slope of our tangent line gets closer and closer and closer to whatever this turns out to be. So that's our limit. So this is how we're going to define the slope of the tangent line. The slope of the tangent line is this limit. So that's our first, not our first, that is the major idea today, is that limit gives us the slope of the tangent line at a particular point. So this lets us calculate the slope of the tangent line at any point on any function, this limit. All right, questions so far? So we worked with a couple of these limits the other day. So I want to go through a couple more today. And then we're going to, because this comes up so often, this limit comes up so often, we give it a special name. We'll talk about that in just a little bit. All right, so let's look at some examples. This limit is our idea. This is the slope of our tangent line at a particular value of x. Okay. So we want to find the slope So we want the slope of the graph of y equals x squared plus 1 at the point 1, 2. So here, x equals 1. And our slope is the limit as h approaches 0, just rewriting this, f of x plus h minus f of x over h. And I'm going to plug in x equals 1. So this is going to be the limit as h approaches 0. F of x plus h equals 1 plus h. So I'm finding f of x plus h, which is 1 plus h squared plus 1. That quantity is f of x plus h. X is 1, and we're plugging 1 plus h in for x, minus f of x, 1 squared plus 1. That's f of x. X is 1. And we're dividing by h. And we're going to multiply this out and simplify. Because if I plugged in h equals 0, I would get 0 over 0, indeterminate form. So that tells me I have more work to do. Yes?
I was confused, like, where did you get, like, 1 plus h squared? Is like f.
F is x squared plus 1. We're plugging in 1 plus h for x. Everywhere we see an x, we're plugging in. This tells us to put in whatever x is. We're putting in x plus h. So since x is 1, I'm plugging in 1 plus h everywhere I see an x. So that's where that 1 plus h is 1 plus h squared plus 1. Okay? All right, then I'm just going to multiply this all out and simplify. So 1 plus h squared is 1 plus 2h plus h squared. I'm just squaring this, multiplying this out. Plus 1, and I'm just going to write everything out here. Minus 1, minus 1. Over h. So multiply this out. This plus 1 is here, minus 1 here, and a minus 1 there. And then I'm going to cancel out everything that I can. So I can cancel out a plus 1, a minus 1, a plus 1, a minus 1. So I get the limit as h approaches 0 of h squared plus 2h over h. Still get 0 over 0 when I plug in h equals 0, but what can I do to this thing? Simplify? And how am I going to simplify it? Factor out an h here in the numerator. H times h plus 2 over h. And then what can I do with these h's? They cancel. H divided by h is just 1. So I get the limit as h approaches 0 of h plus 2, which is 2. So the slope of y equals x squared plus 1 at the point 1, 2 is 2. All right, questions on what we did there? All right, let's look at another one. What we want to do is be able to find the slope of the graph at any point. We don't want to have to just calculate at one point. We want the slope at any point. So let's talk about how we're going to do that. So we want to find the slope of f of x equals 2x squared minus 3 at any point x f of x. So instead of a particular point, we want to find the slope at any point. Then we can just plug in x and we'll have a function that will give us our slope. We'll be able to plug in x and find our slope at any point. So back to our definition. So this is telling me I'm going to plug in x plus h. F of x plus h just says plug in x plus h everywhere I see an x. So this is the limit as h approaches 0 of 2 times x plus h squared minus 3. That value is f of x plus h. I'm just plugging in x plus h for x. Minus 2x squared minus 3. That is f of x. That's what this tells me f of x is. And then I'm dividing that by h. And I'm going to multiply this all out and simplify. So when I multiply this out, I get 2 times x squared plus 2xh plus h squared, that's this squared, minus 3 minus 2x squared plus 3. Just distributing that negative 1 over h. Distribute that 2. So we get 2x squared plus 4xh plus 2h squared. This 3 cancels, and I get a minus 2x squared over h. So that 2x squared cancels. And I get the limit as h approaches 0 of 2h squared plus 4xh over h. Still 0 over 0 if I plug in h equals 0. So what do I do next? I'm going to factor here in the numerator. Factor out that h. H times 2h plus 4x over h. Our goal here is always going to be somehow to manipulate this so I can cancel out that h, so I'm not dividing by 0 anymore. Now those cancel, and I get the limit as h approaches 0 of 2h plus 4x. And as h approaches 0, what does this approach? H is going to 0, so this I can plug in. I don't have a 0 over 0. Nothing crazy happens. So when I plug in h equals 0, 4x. So the slope of 2x squared minus 3 at any point is 4x. So I can plug in x equals 0, 1, 2, 3, plug in whatever I want, and that would give me the slope of my tangent line at any point. All right, questions there? This process of calculating this limit comes up so often in calculus that we give it a special name. It's called the derivative. So what we say is, from the previous example, the derivative of f of x equals 2x squared minus 3 is, we use a prime, f prime of x equals 4x. So we call that function 4x the derivative of 2x squared. And the derivative is the slope of the tangent line. The derivative is that limit that we were talking about. So the derivative of f of x equals f prime of x equals this limit as h approaches 0 of f of x plus h minus f of x over h. That is the definition of the derivative of a function at a particular point. And that the derivative gives us the slope of the tangent line, the slope of the graph at any point. One of the two major ideas in calculus, this idea of a derivative. You'll also see it written dy dx. You'll also see it written y prime d dx of f of x, or d sub x of y. And what this is the rate of change of the function as x changes. Yes?
What happens if there's a variable in the exponent?
If there's a variable, then this limit gets a lot harder to evaluate.
Okay.
So if you had like an exponential function,
Yeah.
then you have to learn more about limits and evaluating limits to figure out how to come up with the derivative of
I was
those
pointing
functions.
like what if it was at 2x to the x?
Right. Or sine x or cosine x.
Yeah.
Those get a lot more tricky.
Okay.
So we're going to work with pretty nice functions to find a derivative. All right, questions? All right, so I want to do a couple more of these, finding derivatives. Go through a couple more examples of finding derivatives of functions. Now I know some of you in your, if you take in physics, Mr. Lowe shows you a shortcut for finding derivatives. When we're finding derivatives in here, if you've learned that shortcut, we're finding the derivative using the definition. You have to use the definition, you have to use the limit to find our derivative. You'll learn more about the shortcut in calculus. All right, so let's look at a couple of examples. We want to find the derivative of x squared plus x minus 2. So we're going to start with our definition. So this is going to be the limit as h approaches 0, f of x plus h squared plus x plus h minus 2 minus f of x over h. This is f of x plus h. This is f of x. And then we're going to use what we know about algebra to simplify this. So it's going to be the limit as h approaches 0 Multiply this out. X squared plus 2xh plus h squared plus x plus h minus 2. I'm just going to write everything we have out here. Minus x squared minus x plus 2 over h. And then I'm going to cancel out everything that I can. I have an x squared and a minus x squared. I have an x and a minus x. I have a minus 2 and a plus 2. So I end up with the limit as h approaches 0 of x squared plus 2xh plus h. No, I don't have an x squared here, do I? H squared. H squared over h. Factor out this common term in the numerator of h. Those cancel. Limit as h approaches 0 of this thing is just 2x plus 1. So the derivative of x squared plus x minus 2 is 2x plus 1. Questions there? So this derivative, again, just to re-emphasize, the derivative is going to give us the slope of this graph at any particular point. And the derivative, like I said, one of the two major ideas in calculus, an important concept, kind of like the limit and kind of like factoring for algebra. Once we have this idea of the derivative, the limit, factoring, those ideas never go away from here on out in math. You'll use factoring for almost everything. Limits come up frequently from here on out in math, and the idea of a derivative is going to come up very frequently from here on out in math. It's one of the big main ideas that we've come up with in math, basically in human history. All right, let's do one more. Little trickier function. F of x equals 1 over x. We want the derivative of this thing. So this is our limit as h approaches 0. F of x plus h, 1 over x plus h, minus f of x over h. So what do I have to do with this function to find this limit? If I plug in 0 over 0, or plug in h equals 0, I get 0 over 0. That says more work to do. So what do we have to do here? Well, since we have these fractions in the numerator, what do we want to do with those fractions? Our technique for finding derivatives is simplifying. One of the ways that we simplify is finding common denominators. So I need to find a common denominator here for the numerator. So I'm going to multiply this by x over x, and multiply this by x plus h over x plus h to get my common denominator of x times x plus h. So then in the numerator, I have 1 minus, not 1, I have x times, or x minus x plus h over my common denominator, x times x plus h over h. I can think of this, and I forgot to write my limit here. limit as h approaches 0. I can think of this as dividing by h over 1. So when I divide by a fraction, I multiply by the reciprocal. So this is the limit as h approaches 0 of x minus x plus h over x times x plus h times 1 over h, multiplied by the reciprocal. It's going to be the limit as h approaches 0. X minus x plus h is minus h over, and here I have an h, I'm just going to multiply this in the front, h times x plus h. What can I do with these h's? Factor of h in the numerator, factor of h in the denominator. Those cancel. And as h approaches 0, now I don't get 0 over 0 anymore when I substitute in h equals 0. And this is minus 1 over x squared. So the derivative of 1 over x is negative 1 over x squared. Questions then? All right, homework tonight, just practicing with some of these ideas. All right, there you go.